Welcome all of you in the last day of this workshop. So, to Dr. Gaurav Bhatnagar for his last lecture.
Okay, thank you, Dilpreet. Good afternoon to all of you. So now let us start the last lecture of this particular series. As I mentioned in the last lecture, that today we are going to see the applications of linear algebra in the diverse discipline, which we are going to have, uh, uh, around us. So let me start discussion on it. So before I start, so my screen is visible to all, and I am audible to all.
Yes, sir. Everything is clear.
Okay. Okay. So then let us start the last lecture in this particular series. Okay. So in the past four lecture, we have seen uh, some of the applications of linear algebra in our you can say in our daily life as well, and then whatever concept we are having in the elementary education, we have seen some of the example from there as well. After that, where we were discussing the applications of linear algebra, specifically the image processing, and in the last lecture we are actually uh, discussed about the singular value decomposition, its properties, and why it is going to be useful in certain applications, especially the image processing. We have seen that. And then we have extended the concept of SVD to different application. One was the pseudo inverse, other one was then we have seen two more application of it. Then finally we have discussed about the principal component analysis, which is going to be the dimensional reduction technique. So now today, in today's lecture, let me give you a brief introduction of the application of linear algebra, basically in the chemistry or the chemical engineering, then traffic flows, electrical circuits, graph theory, and security. So we are going to see today what kind of application linear algebra is going to have in these particular domains. Of course, due to the paucity of time, I'm not able to include the application of linear algebra in the deep learning and machine learning. So I'm just omitting that part as of now. If we are we are going to have some time remaining in the end, then we will try to see those applications as well. Okay, so now let us start with the application in the chemistry or the chemical engineering domain. So now, as the name itself suggests that in chemistry or the chemical engineering, we are actually looking for the chemical equations or reactions which we are going to, which they are going to have in their domain. So let us consider a scenario. So when you try to create some substance, then you have to take some substance, and then whenever you mix in certain conditions, then you are going to get a certainty. So for this particular example, when you take the some amount of substance A and some amount of substance B and some amount of substance T, then when you combine all these three substance all together in certain conditions, then you are going to get some amount of substance D. So now this linear algebra is going to play a vital role in order to understand what are the different substance which we are going to produce, or what are the different quantity of the individual substance which we are going to have, which we are going to take, so that a desired amount of D is going to be required. So in both the scenarios, this linear algebra is going to play a very critical role, and it is going to give the answer to that particular problem. So now let us try to take a very simple problem that in order to create the substance D, what we have to do is we have to take some amount of A, we have to dilute it with the water, and then similarly we have to take some amount of B, we have to dilute with the water. Similarly, we are going to take the substance C, we have to dilute with the water, and then when you mix all these three diluted substances, then you are going to get the substance D. So now we are going to have going to have some information that if we take the 1.5 gram per centimeter square substance of A, then and 3.6 gram per centimeter cube substance of B, similarly 5.3 for C, then we are going to get the 25, about the approximately 25 grams of the substance D. So this is the one case where the researcher actually tried to take the different values of this diluted solution to create to create the 20 approximately 25 grams of the substance D. And another set of researchers or scientists take the different far different and quantities of these particular substances or the solution, and then they are going to get about the 22.36 gram of the substance D. Similarly, another set of researchers try to take the different amount, which are again going to be the closer to this, but they are going to get approximately 28% of 28 gram of the substance D. Now the question comes is, what are the original volume of the substance A, B, and C, which are actually diluted in the water? Because these are the things which are diluted. So the meaning is some amount of some amount of the substance A is already diluted in water. So now we are looking for what is that particular volume of the substance A, volume of substance B, and the volume of substance C. So using these particular three different experiments, now we need to identify what are the actual volume of the substance A, B, and C, which is actually utilized in this particular experiment. Because whenever you look at a certain chemical equation, then in order to get this particular substance D, there is already a predefined values or the volumes of these three substances. So now they just want to know that whether they are going to take the proper substance or not. So now what we are going to do with this? So again, this is going to be gram per centimeter cube. So the meaning is whenever I multiply this 1.5 2x, I am going to get the actual, you can say actual weight of that particular volume or diluted solution. So they are just trying to do this 1.5 multiplied by x, 3.6 multiplied by y, and 5.3 multiplied by z. You are going to get the actual solution which you are going to have for this particular formation of 25 grams of substance D. Then when you add this, then you are going to get this particular thing. So the meaning is this is nothing but an algebraic equation which will tell you that what are the different substances you have taken in this particular experiment. In the similar manner, the second equation will become 2.5 of x and 4.3 of y and plus z, and then is equal to this. In the similar manner, this is going to be this particular scenario, and hence this chemical reaction, in order to find out the actual volume of the substance A, B, and C, we are now getting a system of algebraic equation. So now if I solve this system of algebraic equation where this x, y, and z are the unknown parameters, and when I solve this, I am going to get the actual volumes of these parameters A, B, and C, which are actually being diluted in the water before the chemical reaction was initiated. And hence now you can have the multiple ways to solve this. You can use the Gaussian elimination method, you can use the Jacobi method, Gauss seidel, or any other kind of method you can use to find out the values of x, y, and z. The simplest method is the Gaussian elimination method, so you can use that, and then you are going to have the solution, right? So the Gaussian elimination method, I think everyone is aware of it. You have to find out the augmented matrix, and then it's going to be 1.5, 3.6, 5.3, and then we are going to have 25.07, and then we are going to have for the second equation, it is going to 4.3, 2.4, 22.36, and 2.7, 5.5, 3.2, 28.14. So now you can take this value as the pivot value, then try to make these elements as 0. Then you can take this as a pivot element and try to make this element as 0, and then using the backtracking you are going to identify the solution. So in order then you can immediately solve this particular system of equation which you know how to solve it, and you are going to get the actual volume of the substance X, this A, B, and C, And when you solve it, it is going to be x is going to be 1.5, y is going to be 3.1, and z is going to be 2.2. So this much again this much quantity of the substances A, B, and C you need to consider in order to form 25 grams of a substance D as per the experiment 1, 22.36 gram of substance D as per the experiment 2, and then 28.14 gram of substance D as per the experiment 3. So this is how this system of linear equation, which is going to be a very integral part of linear algebra, is going to play a vital role in the chemical engineering or the chemistry discipline. So this is not the only problem which you are going to have in these two disciplines. Now we are going to have one more problem in which the linear algebra is going to play a remarkable role, and that is called the chemical balancing the chemical equation. So again, so we are going. We already got the columns of this A, B, and C. Anyways, so now next problem is in the same domain is the chemical balancing problem. So now this problem is nothing but the consequences of mass conservation law, which says that you cannot destroy mass and you cannot generate a mass. So what is happening over here is so again, as I mentioned, it's going to be the law of the conservation of mass. Mass is neither created nor destroyed. So whatever mass you are going to have before the reaction, the same amount of mass you are going to get after the reaction. So this particular thing you have to follow. But now in chemistry, there are two ways to look at this particular scenario. One way is just as we have seen in the previous example, then where you are looking at the quantity of the substances. Other one is you can look at the number of atoms involved in the equation. So the number of atoms which are involving in a particular reaction, before reaction and after reaction, the number has to be same. So the equation has to be balanced on the both sides before reaction and after reaction. And whenever you try to apply this conservation of mass law on the in the sense of the number of atoms, then that problem is called the chemical balancing problem. So therefore, in any chemical reaction, balancing of the equation requires the same number of atoms on both sides of a chemical reaction. The mass of all the reactants, the substance going into a reaction, must equal the mass of the product of the substance produced by the reaction. So this problem is going to have the two different dimensions where you are looking at the mass or where you are looking at the atoms. So depending on the situation or depending on the thrust interest in a particular problem or in a particular reaction, you may always go with this particular direction or this particular direction. So let me take one example from the direction of the atoms. So now let us consider this very you can see a very famous chemical reaction equation where these two substances are going to be reacted to give you the water and the carbon dioxide. So now you can look at over here. If I'm looking at the atoms used or atoms of oxygen used before the reaction is going to be 2 atoms. However, after the reaction, what I am getting is I am getting the 2 atoms in the carbon dioxide and 1 atom in the water. So now after the reaction, it will become the 3 atoms of the oxygen. But as I mentioned, that the conservation law says that you cannot create atom or you cannot destroy an atom. So the meaning is these 2 atoms of oxygen before reaction and after reaction has to be same, has to balance. It's in the similar observation you can have for the carbon. Now here I am going to have the 2 carbon atoms and here I am going to have the single carbon atom. Similarly, I am going to have the 6 hydrogen atoms and 2 hydrogen atoms after the reaction. So now we have to somehow balance this equation so that the number of atoms before the reaction and the number of atoms after the reaction is going to be same. So now balancing this chemical equation means mathematically finding the values of these 4 parameters x, y, z, and t so that the number of atoms of each element is the same on the both sides. So basically, I'm looking for this particular equation. So I'm going to take that. I'm going to multiply this whole substance by x, this whole substance by y, and this whole substance with z, and this whole substance with t. And the objective is when I talk about the individual atoms, on the both sides they have to be same. So it is a very simple equating problem where on the both side you are going to equate the total number of atoms of C, the carbon, total number of atoms of the hydrogen, and for the oxygen. So if you do that, you can immediately find out that this particular part will say I have the 2 atoms of carbon, but that is multiplied by x. So the total number of carbon atoms on left hand side or before the reaction is going to be twice of x. However, after the reaction, it is just going to be the z. So the first equation which I got after the equating both sides and the same number of atoms or number of carbon atoms, I am going to get a 2x is equal to z. In the similar manner, if I equate the atoms of hydrogen on both sides, I am going to get the 6x is equal to 2t. Similarly, for the oxygen atom, you can get the 2y is equal to 2z plus t. So now again, when you try to balance the equation, ultimately you are going to have a system of equations. And of course, this system of equation is going to be the homogeneous in nature, and then you are going to solve this particular this particular system of equations, and you are going to get the final answer. And then, as soon as you will get the final answer of it, then you are going to have all the atoms equally participated in both the sides. So now, when you solve this, you can solve it quickly. Again, you can take the Gaussian elimination method or any kind of method. Then you can find out the value that the value of x is 2, value of y is 7, value of z is 4, and the value of t is 6. So the meaning is when I put 2 here, 7 here, 4 here, and 6 here, I am going to get a balanced equation. The meaning of balanced equation is the number of atoms before the reaction and after the reactions are going to be same. And and if you recall the basic maybe the 12th standard or 11th standard time, then you might have done these kind of reactions, and then you are always going to multiply certain substance with some constant. And the reason for this constant is you need to you have to apply the conservation law from the sense of atoms. And hence, every chemical equation has to undergo this process of finding the balancing parameters so that the number of atoms before reaction and the number of atoms after reaction is going to be same. So again, in this chemical engineering and the chemistry domain, the system of linear equations are going to play a remarkable role in many problems, in many situations. And 2 of those situations I just mentioned in today's lecture. So this is how the linear algebra is again going to give benefit to the different domain. So it's all about the chemistry and the chemical engineering. So let's go for the new application where we are going to have the traffic on junctions. So now the traffic flow problem. How this linear algebra is going to give you a better idea for the traffic flows. So now let us consider a hypothetical scenario where or maybe the hypotheticity where we are going to have the 4 different junctions. This is going to be the junction 1, this is going to junction 2, 3, and 4. So now again there are going to be some restrictions on the traffic flow as well. So now in this junction there are 2 intake, one from this direction, other one from this direction. I know the value which are entering for this direction. I don't know the value which are entering for this particular direction. In the similar manner for the junction 2, there are 2 points of the input. One is this particular input, other one is going to be this particular input, and I don't know these values. But I know that final output who are leaving the junction 2, the odd number of vehicles who are leaving the junction 2 is going to be 300. And the similar kind of scenario is given for all the junctions. So now we have to find out what are the traffic flow in these particular routes. So now let me very quickly assume that this is going to be x1, this is going to be x2, this is going to be let's say this is going to be x3, x1, x1. The flow the flow at the function junction 1 is going to be 200 plus xy. So this is an inflow, and the outflow is going to be x1. So at the junction one, the equilibrium of the flows is given by x5 plus 200 is equal to x1, because these are the input to the junction 1 and this is going to be the output at junction 1. In the similar manner, if you consider the junction 2, this x1 is essentially the inflow, x4 is again going to be the inflow, so I'm going to get x1 plus x4 is equal to now the outflow is this x2 is also left from these two vehicles, whatever the amount of vehicles we are going to have, and the 300 is also with there, so it's going to be 300 plus x2. Similarly, on the junction 3, if I look at the equilibrium of the traffic flow, I will get that the inflow or the junction 3 is going to be this x2, this x3, and this is going to be the output. So I'm going to have x2 plus x3 is equal to 50. In the similar manner, when I look at the junction 4, when I look at the junction 4, then I am going to get the inflow of 150 and the outflow of x5, x4, and x3. So I will get x4 plus x5 plus x3 is equal to 150. And hence, when you try to find out the traffic on junctions, it's all about how many vehicles are entered and how many vehicles are left at particular junction. And depending on this inflow and outflow of the vehicles, the traffic lights are going to be regulated. And then if you can observe that at some junctions, the stopping time for sometimes is going to be higher, and at some junction the stopping time is going to be less. So it's all about, on an average, how many vehicles are actually inflow and the outflow at that particular junction, and that will decide that okay, at this junction we have to give the a bigger hold time or the lesser hold time. So now again we are getting a particular system of linear equations. You can immediately solve that, and if you solve that, then you are going to get the inflows at the junctions x1, x2, x3. Sorry, junction 1, junction 2, junction 3, and junction 4. So again, I am not going to solve this particular a system of equation which you can solve easily. So after solving this, you are going to get the flow x1, x2, x3, x4, and x5. So even the regulating the traffic lights is a pure application of the linear algebra, where the system of linear algebra, the system of equation concept of linear algebra will play a remarkable role. And using this inflow and outflow thing, now people will regulate different kind of timing at the different time of junctions. So this is a very simplest application of linear algebra in the traffic flow. So now a similar kind of application we are going to have in the electric circuit analysis, or you can say the in the electric circuit, where we are interested in finding out the current flow in a particular circuit. So let me consider a very simple circuit which is going to have resistance and batteries as well. So this is going to be the circuit where we are going to have the 4 different points. This is going to point A, this is the point B, point C, and this is going to be point D, where A and D are going to be the source and B and C are going to be the junctions of this particular circuit. So now what we are looking at is, we are looking at what is the value of I1, what is the value of I2, and what is the value of I3. So in order to solve this, then we have to go a little bit in physics, and then we know that in physics we are going to have the certain laws which will govern this the flow of the current in a particular circuit. And the very first and the basic law is called the Ohm's law. So Ohm's law, and Ohm's law is going to give you the relationship between the voltage and the current, and it's going to be V is equal to IR. This is going to be one of the most basic law which will tell you the current flow in a particular circuit with respect to the source you are going to have in that particular circuit. The second law which we are requiring to solve this problem is called the Kirchhoff's law. There are going to be the 2 Kirchhoff's laws. So the Kirchhoff's first law. So the Kirchhoff first law is very simple, and it is going to be the equilibrium law, which says that the inflow current and the outflow current is going to be same. So inflow current is equal to outflow current in a particular circuit. So like whatever current I am going to have, so this is going to be the inflow for junction B, and this is going to be the outflow for the junction B. So the meaning is inflow and outflow at this particular junction B is going to be same using this particular. So the essence says that I3 plus I2 has to be I1. So this is nothing but the Kirchhoff first law. Then we are going to have one more law that is called the second law of Kirchhoff, and it is all about the voltage, which says that the algebraic sum of the voltage drop and voltage drop and in the closed loop is going to be the total voltage in the loop. So I'm not giving the exact definition of this particular loop, but when you try to accumulate the current flow in this particular network or the circuit using these with respect to these three laws, then you are going to get the system of linear equation which will give you the current flows. Like in junction B, as I mentioned, that the flow equation is going to be said that I3 plus I2 is equal to I1. This is going to be the first. This is going to the first condition which we are going to have. Now, if you look at this particular circuit, then this I3 current is flowing from this particular resistance over here. So I'm going to get the 10 I3. So this is going to be the current over here. Then I'm going to get the total voltage of 10 volt over it. So then if I use this particular equation and this particular equation, I'm going to get a very simple equation 10 I3, and the direction is different over here. So I will get the minus 10 I2. And then by the third law, it has to be equal to the total voltage available for that particular circuit, and is going to be 10. So in the similar manner, if you look at this particular circuit, then what is going to happen? So it is going to happen now. I1 is going to flow from the 20 ohms. So it's going to be the 20 I1 plus again 10 I2 is common in this circuit and this circuit. So we have to take this again 10 I2, since the dimension or the direction is same. So we have to add them. No need to change the direction, because here the directions are going to be opposite. So we have to take one positive and one negative. So in this case, what I am going to get, and the total source is going to be of the 5 volt. So after this 3 law, I am going to get 5. So hence this is going to get the complete dynamics of this particular circuit. And again, you can solve this to get the final flow or the current in this particular circuit. So when you solve it, again, I am leaving this as a small homework for you. You can do it very easily. Let me give you the final answer. So I1 is going to be 0.4, I2 is going to be minus 0.3, and I3 is equal to 0.7. So now the observation which you need to make is with respect to this I2. So the value of I2 is negative. So the meaning is the direction given in the circuit is not correct. If this is going to be the correct direction, then I am going to get the all positive values. So hence the I2 is running or flowing in this direction rather than this direction. And after getting this value, you can always correct this particular point in the circuit diagram which you are going to have. So again, in this electrical engineering, a lot of applications which you are going to get from the linear algebra. This is one of the simplest glimpse of it. Now there are many other applications in the electrical engineering domain which are going to be utilized this linear algebra concept, like controllability is going to be there. Then there is going to be there's going to be the mathematical modeling, a lot of application of mathematical modeling. Then there's going to be a lot of applications of this signal processing technique, like always uses the Fourier transform, wavelet transform, Z transform. So all these mathematical transform which we are going to have, the discrete version of those, all those transformation are actually applicable in the electrical engineering domain. So the linear algebra is going to have the diverse application in the electrical engineering discipline. And this is going to be one of the simplest example. Okay, so now let us go ahead and then let us try to have the application of linear algebra in the cryptography, or basically the data security, which is going to be which is going to be of the utmost priority nowadays, because everyone is more concerned about their the privacy of their data. So now quickly have the glimpse of this particular application as well. So again, just to brief you, what is the very meaning of the cryptography? So cryptography consists of two words, crypto and graphy, and it is the art of hide a message according to a secret code. So this secret code is usually called the key for the whole process, and this message which you are going to hide it, that is going to be going to be in an intelligible manner, so that no one can observe that particular message. Like if you look at this particular figure, so cryptography you can assume like a black box where you are going to give some meaningful information, and when it comes out from that particular process or that particular box, you are going to get some garbage kind of thing which you are not able to recognize. So basically you are trying to change your data in a form in which no one is going to understand what you are trying to say. Like a very simplest example is going to be, if you have the jigsaw puzzles for your kids. When you are going to have a small kids, they are going to have jigsaw puzzles. You just take all the pieces out. You just mix it up and you just ask kid, okay, now solve this puzzle. So what kid is going to do? He has to identify the correct piece, and he have to put that correct piece in that particular puzzle. And at the end, they are going to solve that particular thing. So this is nothing but a very simplest example of cryptography, where a particular kid is also capable of doing that. However, when we try to do it for our data privacy, of course, the process is not going to be this much simpler, so that a kid is going to crack that. However, that the idea is very pretty simple, that the message which you want to convey, you have to distort in different kind of languages, different kind of forms, so that no one is going to understand your actual message. In the jigsaw puzzle, one image is going to be cut into the different pieces, and those pieces are jumbled up to get the effect of the cryptography. So now in this cryptography, if you look at the application of linear algebra, then this matrix multiplication, or in general the matrix operations, are going to play a vital role in encoding and decoding a given particular message. And this particular cryptography is going to essentially ensure the content protection. So because you are changing the content of your data. So if I say I have 10 or 1001, and I'm now changing it to something else. So basically I'm just trying to secure the content which I'm going to have. Then again, it is going to give the authentication. The meaning of authentication is only the genuine person are going to decode the message from this junk value. So once you encode, when you go from this direction to this direction, this is called the encoding of data. So you are making your data in a form so that no one can understand the data. And whenever you're trying to travel from this part to this part is called the decoding, when you are going to use this form of data to extract the actual message. So that is why the cryptography is going to have two component, encoding and the decoding of the messages which you are going to have. And the authentication comes is only the authentic person who has encoded the data is going to be able to decode the data. So the authentication will also come into the picture. And then let's say I have converted 1001, let's say, in the ABCD. Now no one want to understand that I want to pass on this particular message after looking at this alphabet. Then let's say someone just try to change this C letter with the E letter. So now the modified message is going to be ABED. So now I need to identify if I have some decoded data with me, or sorry, encoded data with me, someone has done bad to the data or not, someone has changed anything in the data or not. So that is called the localization of the modification. So when you try to localize the modification, so it will give you, okay, so this is the place where someone has changed the data. So this is how this cryptography is again going to be used many times for the localization of modification. And when you try to use this cryptography for the localization of modification, that is basically called the hashing. So it is going to be a similar technique on the same philosophies. However, few philosophies are a little bit different. So where we are not looking for the reconstruction of my message. Okay, so these are the three main objective of cryptography which we are going to have. So now let us take how the cryptography is going to work. So this particular figure will tell you a very brief overview of the cryptographic system. So now there are going to be three parties. One party is the sender who just want to send the message, and one party is going to be the receiver who want to receive the message, and there is going to be some interceptor or the intruder who just want to hijack the whole system and then try to get the data which sender is going to send to the receiver. So now sender will take the message. So that message is always called the plain text. Then it will apply it will take some encryption key and some algorithm and convert it into the form so that no one can understand what the actual message is. Now the interceptor is going to have the access to the ciphertext. So this particular intruder or interceptor, what he try to do is he just try to decode this particular text to get the plain text. So now that is why this key and the algorithm which you are going to have is going to play a vital role in the security, so that no one can decode the data without have the knowledge of encryption key. So, after that, this ciphertext is going to be ciphertext means the modified version of the text is going to be communicated to the receiver, and whenever the receiver want to see what the actual message is, so then the inverse part of this encryption algorithm is going to be there, which I am mentioning as the decryption algorithm. Then this key is going to be communicated to the person. He is going to use that key and the reverse process of the encryption algorithm to extract the plain text. And hence this key is going to create a vital role, because without the knowledge of key, you cannot extract the actual message from the modified message. So this is the whole scenario of the cryptography, where the communication is going to happen between the two persons, and some intruder try to hijack the whole system. Okay, so I'm not going to give you very detail of a technical kind of technique over here. So let us try to have a very simple algorithm which is going to give you the overview of the whole process of cryptography. So now let us consider that the sender want to send this message. The Gaurav Bhatnagar is going to the message which they want to send to the receiver. So now how this linear algebra help us in order to understand or in order to encode this data into some other form. So let us try to see. So now this data is nothing but the textual data. The minimum textual data is I'm going to have the alphabets with me, and then when I take the collection of alphabets, I'm going to get the 2 words. So basically this message is going to have the collection of 2 words. So now in order to decode or in order to use the linear algebra concept, because I know that linear algebra works with the numerical values, not for the alphabetical values or the you can say the symbols. So now we have to assign a numerical value to each and every number. So we know that I can assign A as 1 because the position of A in the all alphabets is going to be 1. Similarly, I am going to assign all the numerical value to all the alphabets. And then whenever the space is going to be there, I will assign as 0. So the space in your message is going to be 0. Now, what you will do, you will convert the message as per this data. So the most equivalent form of the message which you want to send in the numerical form is given by just mapping this particular number or the replacing number from the position of that particular alphabet. So now if I look at this Gaurav and Bhatar, 2 words are there. So this Gaurav, I can always write as G is nothing but the 7th position. So I will get 7th position, A is in the 1st position, and so on. So I'm just going to write those numerical assignment to this particular this particular word. So now it is up to you. There are different ways to do it. Now you can construct a matrix out of it. You can construct a diagonal matrix and then try to modify the diagonal matrix. However, when you are going to have the diagonal matrix, then that matrix is sparse in nature. And whenever you are going to have a very big word, so the dimension of that matrix is going to be a little big. So what you are going to do is you are just select a key, and let me say my key is going to be 3. So now I am looking at how many alphabets I am going to extract from this data. So whatever values I am going to get, I am going to make a pair of 3. So this key k is equal to 3 is going to act as the key for me. So what I will say, I will just make I'm just going to make the vectors with this length 3 out of this particular numerical value. This is going to be this. Now using these two vectors, I'm going to construct a matrix, and this is going to be the matrix. And let's say this matrix is going to be A. And hence, this Gaurav word is now converted into a matrix. Now you are good to go with any kind of operations which you might have known for the matrices. You can do that. You can make the square of A, you can multiply A with any other matrix, such that the matrix multiplication is actually existing. And another thing you can take care of. See, in the similar manner, this Bhatnagar word is also going to be encoded into a matrix. So let's say this is going to be the matrix, and I'm saying this is going to be matrix B. Now this k is equal to 3, and using it as a key is going to be very vague kind of key, because someone will take 4, someone will 5. So we are going to look at some kind of concrete key, so that I am able to change this value. So right now what I have did is I have constructed a vector and then reshaped that vector into a matrix. But if I have access to these values, I can immediately identify what are my alphabet, what is my message. So now the next step says that we have to change the values of this particular matrix. And for that, we are going to take another key matrix, which is going to give me the final encrypted data. So let's say this is going to the matrix E. So now the encryption can be done by taking the multiplication of this matrix E and with the matrix A and B. So now, okay, so now you are going in the decrypted, so encoded data is going to be when you multiply A with this matrix E. So you are going to have the original data matrix, and this is with the key matrix multiplied, and okay, the values are far away from each other, and hence using if someone has the access to this particular matrix, he is not able to judge the actual values of the data matrix which we are going to have. Now, if you want to reconstruct your message back from this matrix, what you have to do? You have to go the reverse process. And reverse process says that you have to, using this particular AD is equal to EA, and then if you have to reconstruct A, then you have to multiply by the E inverse on the both sides. And hence, it is essential that your matrix E is going to be invertible. If it is not invertible, then what we are going to do? We have to take another matrix which is going to be invertible. So there are a few questions in the chat box. I will answer after explaining the whole process, how to do when we cannot take 3 as our key. In that case, of course, the simplest option is you will change your key. Either it is going to be a odd number or even number, depending on how many elements are going to be there. You will choose this k is equal to key and try to create a matrix. So basic idea is you have to, the objective says that you have to create a matrix. If the elements are 4, then you will take k as 2. And if the elements are 5, then you can again bifurcate that data into the 4 plus 1, where 1 is going to be the standalone dot matrix, and you are going to have this k is equal to for these 4 elements. So there are different kind of ways, and then depending on the length of the data which you are going to have, you have to deal with it. So this is the simplest way which we can what we can do with this data. Okay, so what I'm telling over here is, in order to reconstruct your message back from this particular matrix, what you will do, you are looking at a invertible key, because without the inverse, I'm not able to extract my original message again, and hence this matrix key has to be inverted. And fortunately, this matrix is going to be invertible, and if you want to do the recursion, you can do that. Okay, so now after the whole process, the Gaurav word is changed into a vector where all the elements are going to be very diverse in nature. You are going to have some positive value, one negative value, and all this. So now, after looking at this value, I cannot give the overview of the actual message which we are going to have as the Gaurav. So again, as I mentioned that for the reconstruction, this matrix has to be invertible. So the inverse of this matrix, let us denote by D, and this is going to be the inverse of this particular matrix over here. So now in the same manner, we can convert the other word as well. So Bhatnagar is also going to be converted into a vector of some positive and negative values. And this is going to be the final value. And hence, the complete word Gaurav Bhatnagar is now written in the form of this particular vector. Now you can imagine, you can observe that I have written this zero over here. So this zero is nothing but the indication that there is a space in my original data, and hence when you try to decode it, you will not touch this particular location. You are just going to take before and after of this particular zero, so that you are going, you know that okay, this particular anything which is there in front of before this zero will give me one word, and after zero whatever it is there is going to give me the another word of my message. So every blank space is going to be represented by zero, and hence you are not going to deal with this zero. You are just going to deal with the values prior to zero and after to zero. So this is how the encryption is going to work. Now you know the inverse of the C. Then using the reverse process, you can reconstruct your message back as well. Okay, so this is all about the cryptography, the application of linear algebra in the cryptography. So I'm not going into the reverse process, but the reverse process is very simple. You are going to take these values, construct a matrix AD, then of the same size, and then multiply by inverse to get the final values. So Dilpreet, can you please tell me the questions which student have asked in the chat box, or I can open it from here. Okay, I can open it up from here. Okay, sure. Okay, so one question was if length of word is not multiple of 3, then how to write matrix of vector length? Okay, then you can choose the appropriate length. If not 3, then it's going to 2, 4, 6, whatever it will be. So you have to look at what is the possibility for this. At least for this data, this 3 is going to be the perfect number. So I have used the 3. But it is not like that you are not going to use that. Okay, so I think no other question is there. So this is the again the very simplest example of linear algebra, application of linear algebra in the cryptography. So now you can play with it. You can have the different kind of modalities. You can have different kind of operation which you know for a matrix and do the encryption. Okay, so now let us go ahead with the last application of linear algebra. That too again in the mathematical domain only, and that is going to be the graph theory. So now I just want to look at the application of linear algebra and graph theory. I think you might have witnessed this application of linear algebra and graph theory as well when you try to have the lecture on the linear algebra and Facebook, because Facebook and this Google is nothing but the graph. They are actually on the graph. But again, I am going to give a very intuitive idea how things are moving in the graph theory as well. So linear algebra will give you a better way to represent the graph, because when the graph is simple and normal, then you are able to represent it with the lines and nodes. However, when you are going to have the millions of nodes and millions of edges, then it is not going to be a viable option for the visualization purpose to have the pictorial representation of that graph. In that case, we are always going to use the matrix representation of the graph. So let's see what are the different matrix representation we are going to have. So for example, let me give the very formal definition of graph. A graph is a collection of two sets, vertices and the edges. So for example, if I take this as my graph, so where I'm going to have the 6 elements 1, 2, 3, 4, 5, which are nothing but the vertices, and then we are going to have some connections. So let me give you the name. Let's say E1, E2, E3, E4, E5, E6, E7, and E8. So now the my graph G is nothing but the collection of two sets V and E, where E is nothing but the set of or the collection of all vertices, and E is going to be the collection of all edges. So V is nothing but a set containing the vertex, and T is nothing but the collection of all edges. So it's going to be E1, E2 up to E8. So this is nothing but the mathematical representation of a graph. So the graph is nothing but the collection of the vertices and the edges, where the edges will represent how two nodes or two vertices are connected with each other, or whether they are connected or not. Okay. So now there are few definitions before we are getting into getting into the application of linear algebra in the graph theory. So the first definition says the adjacent. So now the two vertices U and V are said to be adjacent to each other if there exists an edge between the vertex U and V. So now here I can say that vertex 1 is adjacent to 2 as well as 2 is adjacent to 1 because there exists this particular edge between these two elements. So any two vertices are said to be adjacent whenever there is going to be a edge between them. Incident means an edge E is said to be incident on vertex B if B is the end point of the E. So it doesn't matter it's a starting point or the terminal point, but it has to be an end point. Like if I take this as E, so this edge E is incident on both 1 and 2 because 1 is going to be the one of the endpoint and 2 is again going to be the one of the endpoint. Now degree of a vertex, number of edges incident on a particular vertex V in a graph is called the degree of a vertex. So if I am again looking at the degree of this vertex 2, so total number of edges which are incident on it. So for or the number of edges for which 2 is going to be one of the endpoint. So now I am going to have this edge, I am going to have this edge, I am going to have this edge, and I am going to have this edge. And hence the degree of 2 or this vertex 2 is going to be 4. In the similar manner, using this incidence concept, you can identify what is the degree. Now the self-loop graph, if in a graph, we are going to have one vertex is connected to with itself, then there is going to be a loop. Like if I say that there, if I add one more edge over here, let's say, whose end point and the terminal point is going to be same. For rest of the edges, one point is same, another point is somewhat different from the previous point. But whenever you are going to add the end and the terminal points at the same location, you are going to get the self loop in the graph, and those graphs are called the self loop graph. Then path is a sequence of distinct vertices and distinct edges. Like if I'm looking at what is the path between 1 to 4. So the path means I'm looking at the combination of vertex and edge. So I'm going to say 1, and let me say this is going to be E1, 1, E1, 3, E2, and then 4. So let's say this is going to be E2. So this particular sequence is going to be a path between 1 to 4. So path is nothing but a sequence of distinct vertices and the distinct edges of a graph. Now, the last definition which I want to consider for today's lecture is going to be a similar graph. Two isomorphic graphs are called similar. So let's say I'm going to have two graphs G and H such that if there exists a function f such that f of G is going to be H, then this particular G and H are called to be the isomorphic to each other. And then if two graphs are isomorphic, they are called the similar. So basically I'm just looking at this mapping F, which are going to connect these two graphs G and H. So in order to existence of this F, the first underlying condition is they should have the same number of vertices. Otherwise, it may possible that this F is not going to be a function. It's going to be a relation. So the first underlying condition is both the graphs are going to have the same number of vertices. Okay, so now if you get into the mathematics, then you are going to add some other properties as well. But the idea is in the similar graphs, we are looking for this F. And now if you look at the scenario when these G and H are going to have the thousands of vertices. So now in order to construct this function F, you have to map each and every matrix from vertex from G to H. And then you have to look at the edges as well. So it is going to be a momentum task for us to understand or to get a definition of this F when your graphs are very large. So linear algebra will give you an aid for this situation as well. So let us say linear algebra is going to play the remarkable role in this particular graph theory. So first way is how to represent a graph into a matrix, and that is going to becomes in the from the perspective of the adjacency matrix. So adjacency matrix is going to be the vertex to vertex relationship where you are going to see that whether one vertex is connected with another vertex or not, and then if it is connected, you are going to assign a value of 1. If it is not connected, you are going to assign the value of 0. So if for the same graph, if I am able to identify the adjacency matrix, this is going to be this material matrix. So what I'm going to do is 1, 2, 3, 4, 5, 6. These are the vertices. So again, it's going to be the relationship between the vertex to vertex. So whether vertex 1 is connected to vertex 1, then these two are going to be connected when there's going to be edge. So there are no loops. So I'm going to get 0 over here. whether 1 is connected to 2. If there is a edge between 1 and 2, then these two are connected. So there's going to be one edge between 1 and 2. So I will get 1. And thus in the similar manner, you are going to enter all the entries in this particular matrix, and this matrix is called the adjacency matrix. So this adjacency matrix is going to be the simplest matrix representation of a graph. And now you can look at, if I'm going to have a graph having the thousands of vertices, once the moment I construct the adjacency matrix, then the visualization, for the visualization purpose, I can immediately identify all the properties which I am looking at for that graph, which is not able to visualizable when looking at the graph. So this matrix representation of a graph will give you a better way to represent your graph, so that you are able to identify all the properties of that graph within ease. Okay, so now let us look at how this adjacency matrix is going to give you the different information about a graph. So the first is degree of a vertex. So now you just take a row or whatever, or column, whatever it may be, and try to sum all the elements. And as soon as you do that, you are going to get the vertex, degree of that vertex. So this is going to be the vertex 1. The summation says 2. So the meaning, the degree of 1 is going to be 2. So the meaning is, on vertex 1, there are 2 edges which are incident. So now you are going to take that. This is going to be the 1. This is going to be a 2. So the degree of 1 is going to be 2, because this E1 and E2 are incidented on this vertex 1. And hence, when you take the summation of either rows or columns, you don't need to take the summation of both. Either rows or columns, you are going to get a degree of each and every vertex. Self loop means 1 is going to be connected with 1. So if in the diagonal you are going to get 0, so the meaning is there is no loops in the graph. So this particular representation will tell you whether the self loops are present in the graph or not. Now if we talk about the path of length n, then take the net power of the adjacency matrix and you are good to go with the path. So if I take a square, the power 2 power of a, then I get this particular matrix. Now let us try to understand what is the meaning of it. So I am interested. I'm interested in the path between 1 to 4 of length 2. I am looking for all the paths between 1 to 4 of length 2. Then how to proceed? 1 to 4 means this is going to be 1, this is going to be 2. So now we are going to use the 2 particular edges, so they are going to be a single path. So now you are going to have the corresponding values over here, and you can identify. So these numbers which are present over here, this will give you the total number of paths of length 2 between the 2 vertices. Like if I'm going to take this first combination 1 and 1, here it says 2. So if the meaning is, in the graph, there has to be 2 different paths which starts from 1 and completes at 1. So what are the path, and the length is going to be 2. So 1, I can go in this direction, I will reach to 2, and from 2 again I'm going to reach to 1. So this is going to be the length 2. So this is going to be the path 1 to 1. Is going to be a path between 1 to 1 having the length of 2. In the similar manner, you can move from 1 to 3 and 3 to 1. This is going to give you another path of length 2 between 1 to 1. So now this square of the adjacency matrix will give you the path of length n between any two vertices. If you are looking for n, then you are looking for a to the power n. So this is how this adjacency matrix is very useful in order to identify these properties. And the most prominent usage of linear algebra in graph theory is to check whether the two graphs are similar or not. So let me take these two graphs, and I just want to know whether these two graphs are similar or not. Now you can look at it. Okay, it is after just looking at these two graphs, or the graph representation of graph, I am not able to understand whether these two are similar or not. The first thing which I have to do is I need to identify the function f such that if I say this is g, this is h, fg is equal to h, or f of h is equal to g. So whatever relation I want to find, I can find. If I am able to find this type of relation, then I can say it's going to be similar or not. But the adjacency matrix will give you a very nice way, and it says that if the adjacency matrix of this is AG, and the addressing matrix of this is AH. And if AG is similar to AH, then the underlying graphs are going to be similar. So the meaning is there exists a matrix P such that you can write AG as AHP. So basically, if you are able to identify this relationship among the adjacency matrix, you can immediately say that it is going to be similar in nature. So this is going to be the very simplest example or widely used example of linear algebra in the graph theory. Now let us look at this Facebook graph. So now number of elements are going to be there. If I'm able to find out what are the connection between the two elements, I may not be able to tell after looking at this pictorial representation of this particular graph. For example, if I say I am looking for the all connection between A and B of all lengths, then I may not be able to find out whether A is connected to this element or not, or what are the connection are going to be. I am not able to find out the path in a perfect manner, and hence when I try to represent this Facebook graph in a adjacency matrix form or the matrix form, I can able to identify how many paths are going to be there. If I know there exists a path, then I will look at and work to find out that particular path. Similarly, what are the total connections of A? So if I say this is going to be my vertex A, then how many this vertex A is going to be connected with how many vertices over here? Whether it is connected to all the vertices or not. So whether in the Facebook graph, every vertex is going to be a user. So basically, I just want to know whether the user A is connected with all the users present in the Facebook or not. So this is the meaning of the total connection of A. Or similarly, I can say that whether these two Facebook graph, which are actually dealt with the two different users, this is going to be the user 1 and this is going to be the user 2, are similar or not. Or whether these two person are going to be same or not. So when you are going to have the forensic kind of thing, then this investigation bureaus are actually trying to investigate the identity of a person after comparing it with the known persons or maybe the existing person. So they are trying to see that, like it is something like that. If I have created the two accounts of Facebook, and if I'm going to have the same friends, same posts, same photographs, something like that, then these two accounts are going to be, are belonging to a single person. So the different kind of strategies they can utilize, these investigation bureaus they can utilize, and they try to see the different kind of phenomena, and they're going to tell what are the different ways. Okay, so that is why this linear algebra is going to give me a very better way to represent the graphs. When the number of nodes are going to be very high, number of edges are going to be very high, I am still able to visualize things clearly. So let me conclude this lecture series of mine. So the conclusion says that the modern world would not exist without mathematics in general, and especially with respect to linear algebra. And you are going to find the applications of linear algebra in different kind of diverse disciplines. With linear algebra, you can tell the future, you can build the future, and you can nurture the future. So because if you are going to have the perfect knowledge of this linear algebra, specifically the matrix theory, and this matrix theory finds the numerous application in different disciplines. So you can try to build up the new theories, try to build up the new technologies, and all those things you can do that. And then the bottom line says that linear algebra lies at the heart of all the disciplines. And there is going to hardly there is going to be a single discipline where you cannot find the application of linear algebra. It may be a small application, it may be a big application, but there is no discipline where linear algebra is not used. So linear algebra is widely used in almost all the disciplines. So with this note, I will thank you all for bearing me for this whole lecture series. And again, these are my contact details. If you any one of you want to contact me at any point of time, you can always contact me in over these email IDs. And further details about my profile, you can look at my website over here, which is over here. So thank you very much.
Thank you, Gaurav. Thank you very much for wonderful series of talks. Okay. So, any participants wants to say something, some questions or anything?
So anyone, if you have any query, you can ask me. No issues in that. Or maybe if you want to say something about the lectures, is how it is, whether you like it or not, even you can express your views. So that it is going to be a feedback for me, so that I can improve on myself as well for the future lectures. Okay, so anyway. Okay, I think Dipesh, I think candidates don't have any queries, and even they don't want to share their views. So okay.
Who want to share their views? Sorry. Okay.
Okay.
In
Maybe they are
chat.
writing in the chat box, I guess. Okay. Okay. So thank you all.
Thank you,
For
Gaurav.
thank you.
Okay, so we'll take now 10 minutes break and come back for tutorial.
Sure.
So we'll continue from same link and we'll start at say. Okay. Okay, thank you, Gaurav ji. Thank you very much.
Thank you, Dipesh.